So, welcome to this pre recording of the second half of Lecture 16, scheduled for the middle of week 6, the second half, starting the second half of the middle of week 6, where we continue our exploration of the applications of the Ford-Fulkerson algorithm. So, we have considered the bipartite matching problem, which can be solved in strongly polynomial time by the Ford-Fulkerson algorithm. We now consider an entirely different problem, but related in the sense that there is a interpretation of this problem as a network flow problem, and this allows then to also design an efficient algorithm, although it will be pseudo polynomial time algorithm. Okay, what's the problem that we consider? We have multiple sources and multiple sinks, and we are looking at already a flow network where we have multiple sources which represent factories that produce certain goods considered as supply. The sinks represent retail outlets who have a certain demand. So we can still think of bipartite graphs as in the first part, but this does not necessarily need to be the case. So we can have sinks, sources, but we can also have intermediate nodes, places that have actually neither supply nor demand, but which serve as warehouses. So if there is a demand that is positive, then that node, that vertex serves as a sink. If the demand is negative, then the node, the vertex has supply. So since we know negative numbers, we only need to work with one word, demand, but we interpret negative demand as a supply. So we did something similar before when we were considering profit as a negative cost. So we have a very simple running example with 4 vertices. It's that simple that we identify actually, or we label the vertices with their demands. So we have 2 vertices that serve as supply, that provide supply, that serve as sources. Now you can see that one of these sources can take in has an incoming edge. So it has an incoming edge of one of the factories. So we have 2 suppliers, 2 factories in this network. We have 2 retail outlets. And you can see that one of these retail outlets has only incoming edges, while another one can redistribute. Has also an outgoing edge to a retail outlet. So we have 2 nodes that provide supply with negative demand, and then we have the nodes that have the demand, positive demand. And we have directed edges with integer capacities, which indicates how much flow can exist from one vertex to another. What we want to consider are circulations. So circulations with demands. So circulation is a function which assigns to every edge a non-negative number subject to the capacity condition. So we cannot exceed the capacity that is on every edge. And also everything that goes in must go out. So we have the conservation conditions for every vertex. So we are not going to consider an optimization problem like in the previous part, in the first half of this lecture. We are interested in the feasibility problem. Is there a circulation which satisfies the capacity and the conservation conditions? So, and here for this example, there indeed is. So if you look at red letters, so the first vertex that acts only as a source distributes its supply of 3 to one other factory and 2 go to the value to the vertex that has an amount of 2. That there is another 2 coming from the other factory, that's also 2. So in some sense, the node with demand 2 has excess 2. It only needs 2, but it can send 2 to the last node, which has a demand of 4, and which indeed receives 2 from the second supplier and 2 from the first retail outlet. So we can verify that for every vertex, we actually can add the capacities of the incoming edges. So here we see 4 is 2 plus 2, the 2 red numbers. For the vertex 2, we have 2 incoming, which is 4, but we subtract 2 from the outgoing. So, and that satisfies the demand. So here we have -3, which equals -2 and -1, 2 outgoing edges. Finally, for the fourth, the second factory, we have a supply of 3, a negative demand of -3. So we have 2 outgoing edges, which give the -2 -2, which give you the -4, but this is compensated to -3 by this one incoming edge. So we have, for this running example, a feasible solution, and we can compute this simply by looking at it. But the question is there an algorithm to solve this systematically? Okay, let's first look at some properties. If there is a feasible solution, then that means that all the demands can be met. And then, or we have that also the supply equals the values of these outgoing edges. Pays off to work with one word, demand. So actually we have that the sum of all the demands equals 0. So we are going to prove this property by looking at the conservation conditions. So the conservation condition says that what goes in must go out. So that's simply the statement here. If we look at any edge with U and V, then what goes out is determined outer vertex is the f of out of U, and then we have the f of in of V. So we actually see that we have a cancellation. So what comes in is actually cancels with what goes out in the other sum. So we are summing here over the vertices that are contained in this edge. So we have 2 sums to consider. So we have the sum of the demands of U and V is what goes in. If we first consider V, what comes in, what minus goes out. And that is compensated with, since there is an edge, we have what comes out must be cancelled by what comes in um, by the other. So picture would have actually made this much clearer, but I think we actually sum twice, and once we have a positive, once we have a minus. Because of the conservation, it needs to uh, equal zero. Okay, so the consequence of this, the corollary is actually more important. So, and in some sense, I indicated supply equals demand. If we sum up all the positive demands, the true demands, then this must be compensated by all the negative numbers, which are actually the supplies. So they must equal each other, they must cancel each other out by the previous statement. Then we can denote the sum of all the demands by the capital D. And this must equal, if there is a feasible solution to the circulations with demands problem, this must equal the capital D. So if there is a circulation, then we have this capital D. Okay, so what does this mean now to a flow problem? Well, we can construct a new network where we have all the vertices that offer supply for where the demand is negative. And then we have the set of all the vertices where the demand is positive. We actually consider no intermediate nodes here. Um, we will attach to the first set one super source, and the connections will actually be by edges where the capacity is actually the value of the supply. And now formulated positively or negative the demand that exists at that vertex. You see, for the example, I have two nodes, two factories who each provide supply of 3. So I have added two edges where the capacities equals 3. On the other side, we have two vertices with positive demand. So these are the retail outlets of respectively 2 and 4 demands. So I will make edges, we will add edges where the capacity equals the demands. Okay, and this resembles a graph which we have used also in the previous first part of the lecture, which we also used in the maximum flow. So we have a unique source, we have a unique sink. So and now the problem can be reduced, and that will actually be the main task. We can reduce the feasibility problem to a flow problem. So we have our maximum flow algorithm, or the Ford-Fulkerson algorithm, that will compute a maximum flow. And that's actually the exercise, the last exercise of this lecture. Run the Ford-Fulkerson algorithm on this flow network. While it's a purely computational exercise, it is still very worthwhile doing to try to interpret what it is that you do when you run the steps in the execution of the algorithm to this particular problem with circulation. So what is the interpretation that you can give to the rerouting of the goods, the rerouting of the flow, when you go to an optimal solution? And what is actually the value of this optimal solution? Okay, so here it is. So in some sense, the exercise should have been done before we arrive to this slide. So because we see that if we are computing the maximum flow, then that maximum flow is the capital D. So, and that is the sum of all the demands, the sum of all the supplies. Okay, this is a if and only if, so I should emphasize this. So if we have theorems that are if and only if, these are then directions that go both ways. If we have a feasible circulation, so if we reason about circulation of demands, then we have a maximum flow. And the value of that flow is the capital D. On the other hand, if we have a maximum flow and it has this value, then it can be interpreted as the capital D in a feasible solution. So this is a theorem that establishes the connection between the circulation with demands in a flow network to the maximum flow problem. Okay, let's try to prove this. So it's important to know that if we run the Ford-Fulkerson algorithm, we compute also a minimum cut, and that minimum cut equals the maximum flow. So what does it actually mean if we are having a feasible solution? It sends actually a flow on every edge that is meeting the supply. So that means formulated in terms of demand, there is a flow value that must be equal to the supply. And we also have a flow value that meets demand on the edges. Um, so we're going to summation of, if we want to compute the value of a flow in any solution, you look how much comes out of the source and how much comes into the sink. By conservation, they must be the same. And actually, we see if we do this, if we sum all the edges from the values of the flow, we are actually summations of all the demands. We have this negative values, or reasoning positively over the demands, we have this capital D. So actually what this first statement says is that we are reinterpreting the capital D, the sum of all the demands, in relating to the definition of this added source S star and added sink T star. So a feasible solution gives a flow, a maximum flow of capital D, and that is maximum. You cannot have more because we have actually defined this. And that's also very useful to actually go back to this previous example here. What is this capital D? Well, it is 6 minus 3 plus minus 3, and it is 6 also here, 2 plus 4. So it's important, the examples are actually important to interpret the theorems. All right, now look at the opposite direction. If we have a maximum flow, then actually we have a feasible circulation. Now, if we look at the maximum flow with value D, we actually have that the D saturates every edge coming out of the source and also every edge coming into the sink. So that actually means that we can satisfy all the demands at the supply nodes, all the demands at the demand nodes, where there is, and that means that actually we have the conservation that is met. So if we have a circulation, that was also the definition of the circulation. So we go back to the original graph and we see that the values that were computed by this maximum flow actually gives a circulation with all the conservation conditions that are met. Okay, very good. So the problem is reduced to that. And how much time does it now actually take to compute? Well, we run the Ford-Fulkerson algorithm and we know what is the maximum value of the flow. So that means that that gives an upper bound on the number of steps. And the total number of steps that we need to do is actually the amount of work in every iteration, which we've proven in lecture 15, is actually bounded by the number of edges. We do a search for a path connecting source and sink in the residual graph. That residual graph is at most 2m size. And then among the augmenting path, we are adding, adjusting the flow. So the big C that we were used then was the sum of all the capacities. And here that capital is replaced by the capital D. So we actually, in this added source, we add up all the supplies, or at the added sink, we add up all the demands. Okay, so we have an algorithm where the cost, the running time, essentially is bounded by the size of the numbers. And we stated that this is a pseudo polynomial time algorithm. It might be useful to look at the optimizations we then considered, where we were working with a scaling algorithm. What that scaling parameter delta would actually mean here in in this setting. Now, it's also important that this is a problem that is reduced to Ford-Fulkerson, but in a setting that is actually more favorable, because the bound capital D here, if there is a circulation which exists, it can be computed in advance. The capital C can also be computed in advance, but we have the problem that that capital C is often a bound that is way, way much higher than the optimal value of the maximum flow. So here, if we sum up all the supply, all the demand, we actually do have the numerical value of our capital D. Okay, to end, and I probably will not need that much time here, we can consider not only edges that have upper bounds, but edges that have lower bounds. So this means that you have to use at least some of the connections. So if the lower bounds are zero, then they do not exist. But we consider lower bounds where they are positive. And again, we work with integer numbers. In this course, we deal with primarily discrete problems. That was also, in a sense, important in what was said before. So then we have the capacity conditions that are modified. So this is a modification of the problem. And here now, if we impose a circulation, we must have that certain edges are all already used. Okay, so this is a variation that will be important in the next problem when we consider the survey design problem. Um, the point is that if you have lower bounds, then actually you can eliminate them. So here is a very simple example on how you could do that. If we have a lower bound of 3 and an upper bound, a lower bound of 2 and an upper bound of 3, then we actually can always pretend that we must send always a flow of 2, and that actually decreases the supply by 2. It also decreases the demand at the destination by 2. So we go from 4 to 2, from -3 to -1. So this is a reduction that we claim will actually reduce the problem to a problem with demands and no lower bounds. So it works. If you think about proving by induction, it works if you have one supplier and one retail unit. So, but does it work in general? Okay, so here is the formula. So we have on one edge, we illustrated this. So that was the idea. So now, how will you have a general formula for the demands? So it's easy enough to get rid of the lower bounds. So for the new edges, you have no lower bounds anymore, they're all zero, and you have reduced capacities. Now, how do you recompute the demands? It was a simple subtraction in the previous slide, but in general, you have to take care of the um, conservation conditions. So there is a decreased demand that you have at any vertex if there is an increased flow. So you have to compensate for that. So here are the formulas. You have the initial flow, what related to these lower bounds. If you set them to zero, you actually use them in computing the new demands in your new graph. So here is then the theorem. So we have a flow network with demands and lower bounds on the capacities. So we can derive a new flow network, G prime, so that we have adjusted demands and adjusted capacities. For the capacities, it's a very simple formula. For demands, it looks a little bit more complicated because we use those conservation laws. The point is, and we did some things like this with Dijkstra's algorithm earlier on in the course when we had negative weights, and that was also a simple trick, but then we showed that actually the problem changed. If we were eliminating the edges with the negative weights and then computing shortest paths, the paths were then changing. So the point of this theorem here is that the modifications that we do to the capacities and the demands do not change the circulation. So if we have a circulation, then we actually, in the modified problem, then we have also a circulation in the original problem. So it is again an if only if. So we have to go two directions, starting from a problem in our original problem. We have a flow in the modified network. Okay, so one can see that the value of the flow is actually diminished by these because the capacities are diminishing. So there is actually a very simple formula. You subtract the lower bounds or you add the lower bounds. Okay, let's see what this does. We must have flow. We must actually, if we subtract, are we still going to satisfy the capacity conditions? Yes, that's the easy thing. The conservation conditions require a little bit more work because it requires this definition of these L sub V. So the new demands that are computed here involve this sum of all the lower capacities. And we use the fact, so we go from the feasible circulation on the original problem. So we use this property here that this is here the formula that defines the demand. So I should probably back up a little bit. So for every vertex in the new graph, G prime, we formulate the conservation conditions on the vertices. And then we apply the property that on the original property, we do have a feasible circulation. So actually we are meeting everything. So we are having what comes in goes out. And then the formula that we were proposing to adjust the demands actually subtracts the sum of the lower bounds. And that means that here we have the same conservation conditions on the vertices in the new graph as we did on the original problem. Okay, so that's one direction. Now, in the other direction, if we have computed a feasible circulation in our modified network where we eliminated all these lower bounds, then we can go back to our original problem by adding these lower bounds to the flow. We then also we are going back to the original capacities by adding these lower bounds, and there's still a typo here. This should be an E. Okay, so then we must also verify the conservation conditions, and the proof actually almost goes backwards. So what we do in this proof is actually verifying the definitions, spelling out the definitions, and then apply our recipe using the fact that in our new problem, f prime was actually a feasible circulation. And we have seen this that if we have the conservation conditions that are happening on our new problem, the network G prime, then actually they also hold for the original flow. Okay, so that is it actually. We have actually also integers. So this was very important to prove determination of the Ford-Fulkerson. So everything is expressed with integer arithmetic. If your problem has floating point numbers, then I would suggest that you could try rational approximations. But we assume everything is integer, so we will compute the Ford-Fulkerson algorithm will compute an integer problem, an integer flow, and that flow will actually be equal to the sum of the demands. So here we have now an algorithm that runs in pseudo-polynomial time again, as we observed before. Okay, so this segment goes a little bit faster. I hope it was still clear. Uh, and this is an application. So in some sense, the purpose of the course is that you can start seeing connections between various problems that can be solved in the same time. So again, the transformation to the new G prime happened very quickly. So it was actually depending again on the number of vertices. And the number of vertices in a connected graph is less than the number of edges. So the transformation cost is absorbed in the big O of the running time. Okay, so we are studying an iterative algorithm that runs in stages. So that algorithm is actually no longer strongly polynomial as the size of the numbers matter. In this lecture, so the first half, second half, we took two problems that are seemingly very unrelated and showed that the same algorithm, which is more complicated than all the algorithms that we have seen before week 6, that this algorithm solves it. What is important is here to see the connections between the different problems. And when we were first working, we were having different problems and different algorithms. Here actually we have one same algorithm that can be solving many problems. That's actually the point of this chapter in the course. Okay, I'll stop here. I hope this pre-recording is helpful.